When people hear the word motion, they picture something obvious. A car passing by, a ball flying through the air, a hand moving from one place to another. It feels so basic that it hardly seems worth questioning. Things move. That's the end of the story. Except it isn't. Because the moment you ask a slightly better question, moving compared to what, the ground shifts under your feet. Look around you right now. You feel still. The room feels still. Nothing dramatic seems to be happening. Yet the earth is spinning beneath you at hundreds of meters per second. At the same time, the earth is racing around the sun, and the sun is circling the center of the galaxy, and the galaxy itself is drifting through an expanding universe. All of that motion is happening while you sit there feeling perfectly at rest. So which description is correct? The uncomfortable answer is all of them. Motion does not belong to an object by itself. Motion belongs to a relationship. It only exists when you compare one thing to another. Take away the comparison, and the question, is it moving, loses meaning. That single idea quietly replaces a very old picture of the world. For centuries, people imagined motion as something absolute, as if the universe had an invisible grid marking what counts as truly moving and what counts as truly still. Physics abandoned that picture, not because it was unfashionable, but because nature refused to cooperate with it. Every experiment tells the same story. You can describe motion only by choosing a reference. A train, the ground, the earth, the stars, each choice tells a different, equally valid story. Physics keeps working in every one of them. This already explains something you've felt your whole life without naming it. When a plane cruises smoothly, motion fades from awareness. No special sensation announces speed itself. Only changes in motion, starts, stops, turns, make themselves known. The body responds to acceleration, not motion alone. That observation turns out to be a deep clue. It suggests that motion is less about where something is going and more about how its state changes. Speed becomes secondary. Relationships take center stage. What matters is consistency between descriptions, not a privileged viewpoint. Once you see motion this way, it stops being a simple idea and starts acting like a principle that organizes all of mechanics. It connects walking across a room to planets in orbit, and it does so without ever asking who gets to be really at rest. That question fades away, and a better one takes its place, one that pulls you forward because answering it reshapes how every movement in the universe is understood. And once that idea settles in, that motion belongs to relationships rather than objects, we can finally take it apart carefully and see how it actually works, without leaning on intuition, where intuition tends to mislead. Think about a train moving along a straight track at a constant speed. Inside the train, someone stands up, tosses a ball straight upward, and catches it again. To the person on the train, the ball goes up and comes down in a straight line. Nothing surprising happens. The motion feels ordinary. Now imagine watching that same event from the platform as the train passes by. From there, the ball follows a curved path through the air. It moves forward along with the train, while also moving up and down. Two observers, two different descriptions, one single event. Neither description is more correct than the other. This example matters because it exposes a hidden assumption most people carry without noticing. The idea that there must be one correct account of how something moves. Physics gives that idea up. Motion does not come with a built-in label telling you which viewpoint is privileged. What matters is internal consistency. As long as measurements made within a chosen reference agree with each other and obey the laws of physics, that description stands on equal footing with any other. This is the central mechanism behind motion in physics. Motion is the change of position relative to a chosen reference as time passes. That sentence may sound plain, but every word carries weight. Position requires a coordinate system. Change requires comparison. Time provides the ordering. Remove any one of these, and the idea stops working. This explains why the question, "Is it really moving?" leads nowhere. Really compared to what? Compared to the ground? Compared to the sun? Compared to the center of the galaxy? Each answer produces a different number, and none of them cancels the others. This is where everyday intuition breaks down. Daily experience suggests that motion should announce itself. Something moving should feel different from something at rest. Yet constant motion produces no internal signal. A smoothly moving train, plane, or spacecraft behaves the same way as one sitting still, provided no turns or speed changes occur. Physics does not find this surprising, common sense does. What stands out instead are changes in motion, sudden starts, sudden stops, curving paths. Those events create sensations, forces, and measurable effects. The body responds to acceleration, not to motion itself. That distinction explains a great deal. Early thinkers believed motion required continuous effort. If pushing stopped, motion should fade away. That belief felt obvious because friction is everywhere in ordinary life. Floors, air, roads, and materials constantly interfere. Once friction is accounted for, the picture changes. Remove interference, and motion persists on its own. Objects in space continue moving for enormous distances without slowing. No force is needed to keep them going. Force enters the story only when motion changes, when speed increases, decreases, or direction bends. From the viewpoint of physics, motion is not something that must be maintained. It is something that must be altered. This is why the laws of motion are written the way they are. They describe how changes occur, not how motion exists. They focus on acceleration because acceleration reveals interaction. It tells you when something external is acting. At a fundamental level, motion is the natural behavior of objects in space and time. What feels like rest is simply a shared motion between you and your surroundings. Once this idea is accepted, many familiar puzzles dissolve. Why does a dropped object fall straight down inside a moving vehicle instead of landing behind you? Because it already shares the vehicle's motion before it is released. No invisible push is required to keep it moving forward. Motion continues unless something interferes. Why do passengers not feel Earth's rotation? Because everything nearby shares that motion as well. Without a difference to compare against, motion leaves no trace. This relational nature of motion also explains why physics places such importance on reference frames. A reference frame is not a physical object. It is a bookkeeping choice. It defines how positions and times are labeled. Change the frame, and the numerical values change, but the underlying behavior remains consistent. Physics does not search for the correct frame. It demands that the rules connecting frames agree with each other. At everyday speeds, those connections are simple. Velocities add in a familiar way. At very high speeds, the connections become more involved, and space and time begin to intertwine. But the core idea remains untouched. Motion has meaning only within a chosen reference. Now it becomes possible to say what motion is, not just what it does. Motion is a description of how spatial relationships evolve over time under the constraints imposed by the laws of physics. It is not an ingredient added to objects. It is not a force acting upon them. It is a way of accounting for change. That description might sound abstract, but it is grounded entirely in measurement. Positions are measured. Time is measured. Motion is the comparison between them, and this leads to an unexpected conclusion. Motion is not something that happens inside space. It is part of what gives space and time their physical meaning. Without the possibility of motion, space would have no operational definition. Without time, change could not be ordered. Motion ties them together. Once this is understood, talking about motion becomes easier, not harder. One no longer asks whether something is moving in an absolute sense. One asks how it moves relative to a chosen reference, how that motion changes, and what interactions are responsible for those changes. That framework is powerful enough to describe falling objects, orbiting planets, flowing rivers, and light crossing the cosmos. It does so without invoking hidden backgrounds or privileged viewpoints. And it leaves you with a question that naturally follows, not as a tease, but as a logical consequence. If motion itself carries no special status, and only changes in motion reveal interaction, then what exactly governs those changes, and why do they take the forms they do? That question does not step away from motion. It grows directly out of understanding it well enough to explain it to someone else. Once motion is understood as a relationship rather than a possession, the consequences begin to stack up, and some of them run directly against how people expect the world to behave. One of the first surprises is this: motion by itself does not explain anything. It describes, but it does not cause. Knowing that something is moving tells you where it is relative to something else as time passes, but it does not tell you why it keeps doing so or why it ever changes. That role belongs to interaction. This immediately overturns a common mental picture. Many people imagine motion as something fragile, something that needs to be constantly supported. Physics finds the opposite. Motion persists naturally. What requires explanation is deviation from it. This leads to a result that feels backward at first. A force does not give an object motion, it gives an object change in motion. Speeding up, slowing down, turning, these are the signatures of interaction. Motion itself is the default state. Once this is seen, the universe begins to look less like a collection of moving things and more like a web of relationships that remain consistent unless something interferes. Here is where a paradox often appears. If motion is always relative, how can effects that depend on motion be real? How can collisions matter? How can energy transfer matter? How can momentum be meaningful? The answer is that while motion has no absolute owner, relationships do. When two objects collide, what matters is their motion relative to each other. That relationship determines outcomes. It determines how momentum is shared, how energy is redistributed, and how directions change. No observer disagreement erases those results. Different observers may assign different speeds, but they all agree on what happens next. This agreement is the hidden backbone of physics. It is also why motion connects directly to deeper principles. Conservation of momentum, conservation of energy, and the structure of forces all rely on the same relational idea. They do not depend on absolute motion. They depend on consistency across descriptions. Once you see this, a surprising unification appears. Motion, inertia, and force are not separate topics. They are different ways of talking about how change is constrained. Inertia describes resistance to change. Force describes interaction that produces change. Motion describes how position evolves when change occurs or does not occur. Together, they form a single story about how the universe manages change without contradiction. This also explains why time plays such a central role. Motion cannot be defined without time, and time cannot be measured without change. A clock is not a device that detects time directly. It detects regular motion or regular change. Time gains meaning through motion. This creates a deep link between motion and causality. Causes precede effects because motion orders events. Without ordered change, cause and effect collapse into confusion. Now consider a result that feels unsettling until it is fully absorbed. If motion has no absolute status, then rest has no absolute status either. Being at rest is simply sharing motion with nearby objects. This means the universe does not privilege stillness. Stillness is not special, it is merely common motion. This matters because many everyday explanations rely on an imagined background of rest. Physics does not use that background. It uses relationships instead. From this perspective, even large-scale motion loses its drama. The Earth's movement around the sun is not something that must be justified by an external reference. It is a relationship maintained by interaction. Remove the interaction and the relationship changes. This brings meaning into focus. Motion is not about where something goes in an empty arena. It is about how relationships endure or change under constraints. Those constraints are the laws of physics, and they exist to ensure that no description breaks consistency with another. This is why physics places such weight on symmetry between observers. If the laws favored one viewpoint over another, motion would become arbitrary. Explanations would fracture, prediction would fail. Instead, the universe enforces agreement. Once motion is seen this way, its meaning becomes clearer without becoming mystical. Motion tells us that the universe allows change, but only in ways that remain compatible across all valid perspectives. It allows variety without chaos. It allows difference without contradiction. This also reframes how we think about explanation itself. To explain motion well is not to say this thing moved because it was pushed. It is to say, given these relationships, these interactions, and these constraints, this evolution had to occur. That kind of explanation does not rely on imagery. It relies on necessity, and that is the deeper consequence. Motion is not just a topic within physics. It is one of the conditions that makes physics possible. Without motion, there is no measurement. Without measurement, there is no law. Without law, there is no understanding. Motion sits at the base of the entire structure. So when someone truly understands motion, they no longer think of it as an everyday word describing visible movement. They think of it as a rule-governed description of change, anchored in relationships, protected by consistency, and woven directly into space and time. That understanding allows them to talk about falling objects, orbiting planets, flowing rivers, and accelerating vehicles using the same ideas without patchwork explanations. And more importantly, it allows them to explain motion to others without appeal to authority or memorized rules, because they understand what motion means and why the universe treats it the way it does. At that point, motion stops being something that merely happens. It becomes something that reveals how the universe holds itself together. Motion no longer appears as a simple topic placed at the beginning of physics for convenience. It stands out as a foundation that supports nearly everything else. In physics, motion does not describe an extra feature added to objects. It describes how relationships between positions evolve over time under rules that apply everywhere. With that perspective, ideas that might seem separate begin to form a single structure. Objects continue moving unless interactions alter their motion. Forces describe how motion changes, not how it exists. Mass measures resistance to changes in motion. Reference frames provide different descriptions without changing physical outcomes. These ideas are not independent statements. They reinforce each other. What physics truly knows about motion comes from repeated observation and testing. No experiment has ever identified absolute motion. Constant velocity cannot be detected from inside an isolated system. Changes in motion always reveal interaction. The same laws hold in every inertial frame. These are not philosophical preferences. They are conclusions enforced by evidence. Motion also connects directly to conservation laws. Momentum remains conserved because physical laws do not favor one position over another. Energy accounting remains consistent because motion evolves through time without hidden exceptions. These connections are precise and measurable, not interpretive. There are limits to what is known. Physics does not yet know whether motion can be explained by something more basic, or whether space and time themselves emerge from deeper structures. It is not known whether future theories will revise how motion is described or simply sharpen existing descriptions. What is certain is that any future theory must still account for the relational nature of motion and the absence of privileged viewpoints. This explains why motion appears everywhere in physics. It is not taught early because it is simple, but because nothing functions without it. Understanding motion this way simplifies explanation without oversimplifying reality. Falling objects, turning vehicles, orbiting planets, and traveling light can all be described using the same core ideas applied under different conditions. The differences come from interaction, scale, and reference, not from separate rules. The practical takeaway is direct. Explaining motion does not require asking whether something is truly moving. It requires asking three specific questions: relative to what, over what time, and under which interactions. Those questions are sufficient to describe every case motion physics currently addresses. This approach replaces guesswork with reasoning. It allows motion to be explained clearly to others without memorized rules or appeals to authority. It also explains why physics works consistently across laboratories, vehicles, planets, and galaxies. Motion shows that the universe allows change while enforcing consistency across viewpoints. That consistency makes prediction possible and explanation reliable. With this understanding, motion is no longer just an everyday word tied to visible movement. It becomes a structural idea that supports mechanics, astronomy, and modern physics alike. That is the value of understanding motion properly. Movement becomes something that can be explained everywhere it appears, using the same underlying ideas. The word field carries a strange reputation in physics. It often sounds abstract, almost secondary, as if it were a mathematical convenience rather than something real. Objects feel tangible. Motion feels immediate. Fields can seem like an extra layer, added only after things become complicated. That impression turns out to be backwards. Fields are not an advanced decoration placed on top of physics. They are one of the main ways physics explains how the universe actually works. The puzzle appears immediately. If fields matter so much, why do they not announce themselves in everyday experience? Why does a table feel solid while a field feels invisible? The answer begins with how physics once described interactions. Early explanations focused on direct contact. One object pushed another, pulled another, collided with another. That picture works well when things touch, so it felt complete. Then nature introduced situations that refused to fit. A magnet attracts iron without touching it. An electric charge influences another charge across empty space. Gravity acts between Earth and Moon with nothing visible in between. Something influences motion where no object seems to be present. For a long time, this influence was described as action across distance. That phrase sounded like an explanation, but it avoided the real issue. It said that something happened without saying what existed in between. Fields entered physics as a way to take that in-between seriously. A field assigns a physical condition to every location in space and time. That condition determines how an object placed there will move or respond. Instead of asking how one object reaches another, physics asks what the surrounding space is like at each point. This is the core idea. Space itself carries information about influence. When a charge exists, the space around it has an electrical condition. When mass exists, the space around it has a gravitational condition. Other objects respond when they occupy those regions. This removes the need for distant objects to communicate directly. Each object interacts only with what exists locally, right where it is. Once this idea is accepted, many things suddenly fit together. Electric forces, magnetic effects, gravitational attraction, and light all find a place within the same framework. Each corresponds to a field with its own behavior, its own rules for how it changes and how it influences motion. Fields also solve a deeper issue. They allow interactions to propagate through space rather than appear instantly everywhere. Changes travel. Causes remain connected to nearby effects. Physics regains locality. At this point, the idea of empty space becomes less simple than it once seemed. Even regions with no particles still possess physical properties. Fields can exist there. They can store energy. They can influence motion. This leads naturally to a question that refuses to stay small. If fields fill space and guide how objects behave, where does reality truly reside? In the particles we see, or in the conditions of the space they move through? That question is not decorative. It determines how modern physics understands forces, motion, and even what it means for something to exist at all. That question pulls attention forward because the idea of fields only becomes solid once it is anchored to something concrete. So let's ground it. Take gravity, not as a formula, not as a law written on paper, but as something that actually happens. You release a ball and it falls. That event feels simple. The usual story says, Earth pulls the ball. End of explanation. But notice what that story hides. The ball does not touch Earth. There is empty space between them. If influence passes from Earth to the ball, it must pass through that space. Physics does not allow influence to leap over space without accounting for what happens in between. This is where the field enters, not as a metaphor, but as the thing doing the work. At the most fundamental level, a field is a physical quantity assigned to every location in space and time. Each location has a value, even if no object is present there. That value determines how an object would respond if it were placed there. That sentence is dense, so let's unpack it carefully. A field exists everywhere, not only where particles happen to be. It does not wait for an object to arrive in order to exist. It already assigns conditions to space itself. Objects respond locally to those conditions. In gravity, the mass of Earth establishes a gravitational field throughout the surrounding space. The ball does not feel Earth directly. It responds to the gravitational condition of the space it occupies at that moment. As the ball moves, it encounters different field values, and its motion changes accordingly. Nothing reaches across space. Nothing acts at a distance. Everything happens locally. This is the core mechanism. Once this idea is absorbed, many familiar effects stop feeling mysterious. Electric charges influence other charges because the space around them carries an electric field. Magnets influence iron because the space around them carries a magnetic field. Light exists because changes in electric and magnetic fields travel through space. Fields are not carriers of messages between objects. They are the environment in which objects exist. Here is where common sense begins to resist. Everyday thinking treats space as empty, passive, nothing more than a stage where events occur. Fields overturn that picture. Space itself acquires physical properties. It can be stretched, distorted, energized, and altered. This does not mean space turns into a substance. It means space has measurable conditions that affect motion. A helpful analogy, limited but useful, is temperature in a room. Temperature assigns a number to every location. A cup of water placed in one part of the room warms or cools based on the local temperature. The water does not communicate with the heater across the room. It responds to the condition of the air right where it sits. A field works similarly, except the number it assigns determines force, motion, or energy rather than heat exchange. This analogy exposes where intuition fails. Common sense expects influence to come directly from objects. Physics shows that influence comes from fields already present in space. Objects modify fields, fields guide motion. Once this is understood, the role of particles changes. Particles no longer serve as tiny sources that reach out to one another. They become localized excitations interacting with fields. This is not interpretation layered on top of equations. It is how modern experiments are described. In fact, physics has gone even further. In contemporary theories, fields are treated as more fundamental than particles. Particles appear as localized disturbances of underlying fields, not as independent building blocks. That idea sounds radical only because everyday experience hides fields so effectively. Now consider a classic experiment that makes fields unavoidable: electromagnetic waves. When an electric charge accelerates, something propagates through space and can be detected far away. No particles travel from the charge to the detector. What travels is a change in the electromagnetic field. That change carries energy and momentum. It can move objects. It can heat matter. It can trigger chemical reactions in your eyes. Light itself turns out to be a field phenomenon. This result leaves no room for fields to be bookkeeping tools. They carry energy. They evolve over time. They influence motion. Those are physical traits. Another place intuition breaks is the idea of emptiness. In field theory, space without particles is not featureless. Fields still exist there. They can fluctuate. They can store energy. They can interact. This explains why removing all matter from a region does not remove physics from it. Fields remain. Effects remain possible. At the most basic level, then, a field is a way physics assigns structure to space and time. It tells space how objects will behave and tells objects how to move without direct contact. Fields answer a question objects alone cannot answer: how influence travels and how it remains local. That is why fields appear everywhere once they are introduced. They unify forces. They connect motion and interaction. They replace distant action with local response. And this leads to a deeper consequence that follows naturally rather than dramatically. If fields define the physical condition of space, then understanding the universe means understanding how those conditions change, interact, and constrain motion. Objects become participants in a larger structure rather than isolated actors. That idea does not reduce the importance of particles. It places them where experiments consistently put them, as localized features within an extended physical environment. With this understanding, talking about fields becomes easier, not harder. One stops asking where the force comes from and starts asking what the field is doing at each location. That question has precise answers, and it leaves behind a puzzle that grows directly from everything said so far. If fields fill space and carry energy and influence, what governs their behavior, and why do different fields follow different rules? That question emerges naturally from understanding what fields are, not from adding anything extra. Once fields are accepted as real physical features of space, rather than as mathematical conveniences, their consequences begin to stack up in ways that quietly overturn familiar expectations. One of the most striking results is this: influence no longer belongs to objects alone. It belongs to space itself. A charge does not carry its electric influence like a personal possession. A mass does not carry gravity tucked inside it. Each establishes a condition around it, and that condition exists whether or not another object is nearby to notice it. This changes what it means to explain anything in physics. Instead of saying, this object acted on that object, the explanation becomes, this configuration of the field led to this behavior. The cause is not a hidden push. The cause is the state of space at each location and how that state evolves. At first, this sounds like a subtle rephrasing. It is not. It resolves a paradox that haunted physics for centuries: how something here can affect something far away without violating causality. Fields answer this by refusing to let influence leap across space. Every effect travels through neighboring regions. Nothing skips steps. This immediately ties fields to time. A field does not merely exist, it changes. Those changes spread at finite speeds. Light is the most familiar example, but it is not unique. When a mass moves, the gravitational field around it adjusts. That adjustment propagates. Distant objects respond later, not instantly. Cause and effect remain ordered because fields evolve locally. Here, intuition often stumbles. Everyday reasoning expects the source to do something to the target. Fields insist that the source alters space, and the target responds to the space it occupies. The action is indirect, but complete. Another surprising result follows. Fields themselves store and transport energy. This point cannot be softened. Experiments force it. Light carries energy across empty regions. Electromagnetic fields can exert pressure. Gravitational waves transport energy between massive systems. These effects cannot be explained unless fields are treated as physical entities with energy and momentum. This reshapes conservation laws. Energy is no longer tracked only by watching objects. It must also be tracked in space itself. Energy can move without matter moving. A region can gain or lose energy purely because the field there changes. Once fields are included, conservation becomes exact again. Without them, it appears violated. This is not a technical detail. It reveals a unified picture. Motion describes how objects respond to local field conditions. Forces describe how field conditions vary across space. Energy describes how those conditions are distributed and transformed. None of these ideas stand alone. Fields tie them together. A deeper unification appears when multiple fields are considered at once. Electricity and magnetism merge into a single electromagnetic field. What once looked like two forces becomes one structure viewed under different circumstances. Light appears as a self-sustaining change in that structure. This result was not guessed. It was forced by consistency. Without fields, the connection makes no sense. With fields, it becomes unavoidable. Gravity extends the idea even further. Mass alters the gravitational field, and objects follow paths shaped by that alteration. Modern descriptions go so far as to link the gravitational field to the geometry of space and time themselves. The details grow complex, but the organizing principle remains unchanged. Local conditions guide motion. At this stage, a deeper question arises naturally, not as philosophy, but as consequence. If fields exist everywhere, even where no particles are present, then what does empty space mean? Physics answers carefully. Space without matter is not featureless. Fields remain. They can fluctuate. They can carry energy. They can influence future events. Removing particles does not remove physics. This result feels counterintuitive because everyday experience treats emptiness as absence. Fields replace that idea with structure. Space becomes an active participant. This perspective also resolves another apparent paradox: how particles can behave as both localized and extended. In modern physics, particles appear as localized excitations of fields. The field provides the extended structure. The particle marks where activity is concentrated. Nothing mystical is added. The description simply moves to the level that experiments demand. With this shift, explanation itself changes character. Instead of asking which object caused an effect, physics asks how a field configuration evolved. Instead of tracking invisible pushes, it tracks measurable conditions across space and time. This approach applies cleanly to atoms, circuits, stars, and galaxies without changing its language. That scalability is not accidental. It signals that fields capture something essential. At this point, the meaning of a field can be stated plainly. A field is a physically real assignment of quantities to space and time that determines how objects behave locally and how influence propagates. It exists independently of whether matter occupies a given location. This definition matters because it explains why physics relies on fields so heavily. Without them, influence has no place to exist. With them, locality, causality, energy conservation, and motion align into a single framework. Understanding fields reshapes how reality itself is viewed. Objects no longer sit inside space as independent actors. They participate in an environment that they both affect and respond to. Space ceases to function as a passive background and becomes part of the physical story. Objects are not erased by this view, they are placed in context. The consequence is practical rather than abstract. Once fields are understood this way, explanations become transferable. The same reasoning explains why a compass turns, why light travels, why charges interact, and why gravity guides motion. No special cases are required. No invisible mechanisms are invoked. That marks the transition from knowing how fields behave to understanding what they mean. Fields show that the universe organizes influence locally, spreads change through space, and then forces consistency without shortcuts. They explain why physics can describe interaction across vast distances without contradiction. With that understanding, fields no longer appear as an advanced topic set aside for later study. They appear as one of the basic ways interaction is possible at all. Fields occupy their proper place in physics, not as an added layer, but as a structural support. They provide a way to describe influence, motion, and energy that remains consistent across distance, scale, and perspective. A coherent picture follows naturally. Objects possess mass, charge, and other properties. Those properties establish fields throughout space. The fields assign physical conditions to each location. Other objects respond to those conditions locally. Motion follows from how those conditions vary across space and evolve through time. Nothing in this picture acts alone. Objects and fields form a coupled system. Objects shape fields. Fields guide objects. Physics relies on both because experiments demand both. What physics knows about fields is substantial and precise. It knows how electric, magnetic, and gravitational fields behave. It knows how they change, how they carry energy, and how they influence motion. It knows that changes in fields propagate at finite speeds. It knows that conservation laws remain valid only when fields are included. These conclusions are enforced by measurement. Physics also knows that fields can exist without matter present. Regions of space with no particles still possess physical properties. Fields there can store energy and influence future events. Removing matter does not remove structure. What physics does not yet know is whether all fields arise from a smaller set of principles or whether they are fundamental in their own right. It does not yet know how gravity fully fits with quantum descriptions of other fields. It does not know whether space and time themselves emerge from something deeper. Those unknowns define the frontier, not the foundation. What remains secure is the role fields play in explanation. Any deeper theory must still account for local influence, finite propagation, energy stored in space, and consistent behavior across observers. This understanding changes how familiar phenomena are interpreted. A compass turning reflects a magnetic condition at its location. Light reaching the eye is energy carried by a changing electromagnetic field. Gravity guiding planets reflects motion shaped by the surrounding gravitational field. The same reasoning applies everywhere. Explaining interaction no longer requires imagining distant objects acting directly on one another. It requires describing the field present at a location and how it changes. Fields also alter how space itself is understood. Space possesses physical conditions that matter. It participates in how motion unfolds. It stores and transfers energy. This gives space a role without turning it into a substance. Seen this way, fields are not abstract additions to physics. They are one of the basic structures that make motion, force, and energy intelligible at all.
You spent 3 hours yesterday learning something important. This morning, you can barely remember the main points. By next week, it'll be gone completely. This isn't a focus problem. It's not age. And it's not because you're not smart enough. In 1951, a 33-year-old physicist named Richard Feynman accepted a teaching position in Brazil. He walked into classrooms at the Centro Brasileiro de Pesquisas Físicas expecting eager students. What he discovered instead was a learning catastrophe so complete, so universal, that it explains why your brain is deleting everything you're trying to learn right now. This comes from Feynman's documented account in Surely You're Joking, Mr. Feynman. The mechanism he uncovered doesn't just explain forgetting. It reveals the invisible difference between people who retain knowledge for life and people who pass exams but remember nothing. By the end of this, you'll know exactly why your brain betrays you. More importantly, you'll have the specific method Feynman used to make knowledge permanent. The story begins with Feynman stepping off a plane in Rio de Janeiro. He'd been invited to teach physics for a year. These were serious students at a prestigious institution. They attended lectures, they took notes, they studied textbooks, they passed exams with high marks. Feynman's first few lectures went smoothly. Students nodded. They asked questions using the right terminology. Everything seemed normal. Then Feynman did something unusual. During a lecture on polarized light, he asked a student to explain what they'd learned the previous week about Brewster's angle. The student stood up and recited perfectly. Brewster's angle is the angle at which light reflected from a surface is completely polarized. Textbook perfect, word for word. Feynman asked, "What does that mean?" Silence. He tried again. "Can you give me an example? What surface? What would I see?" The student looked confused. Other students shifted uncomfortably. Nobody could answer. They had memorized the definition flawlessly. They could recite it under exam conditions. But they had no idea what it meant. You've done this. You memorized formulas for calculus but couldn't explain why integration works. You learned accounting principles but panic when someone asks you to apply them to a real scenario. You read that business book everyone praised, highlighted passages, then couldn't summarize the core idea a month later. Your brain stored the words perfectly. It deleted the understanding completely. Feynman started testing this systematically. He'd ask students to explain concepts in different words, to apply principles to new situations, to describe what they'd actually see if they performed an experiment. Same result every time. Perfect recitation, zero comprehension. But here's where it gets worse. These students had spent years in this system. They'd passed hundreds of exams, they had credentials, they looked educated, but Feynman discovered they couldn't answer a single question that required actual thinking. He found textbooks where students had underlined passages. When he looked closer, he realized they were memorizing which sentences to underline based on previous exams. Not because they understood why those sentences mattered. One textbook chapter started, "Triboluminescence is the phenomenon where light is emitted when crystals are crushed." Students had this memorized. Feynman asked if anyone could name one substance that was triboluminescent. Nobody knew. The textbook never mentioned actual crystals, just the word crystals in abstract. These students could define triboluminescence perfectly. They just had no connection to reality. The same principle destroys your retention today. You attend that conference, take notes on key frameworks, then can't remember a single actionable insight 3 days later. You complete that online course, get the certificate, then freeze when someone asks you to actually use what you learned. Your brain is doing exactly what those Brazilian students' brains did. It's storing symbols without connecting them to meaning. Feynman was baffled. How could an entire educational system produce this result? Then he attended other professors' lectures. He watched how they taught. He examined their textbooks more carefully. He discovered something disturbing. The professors were teaching the same way they'd been taught. They'd lecture about dielectric polarization without ever explaining what a dielectric was or why anyone cared. They'd write equations on blackboards without connecting them to anything students could see or touch. Students copied these equations. They memorized them. They reproduced them on exams. But the equations were just shapes on paper, disconnected from physical reality. Feynman called this cargo cult science in his later Caltech commencement address. The students had the appearance of learning, the notebooks, the terminology, the exam scores, but none of the substance. Like cargo cult members building fake airstrips hoping planes would land, these students were going through learning motions, hoping knowledge would appear. It never did. This explains why you forget. Your brain doesn't delete information randomly. It deletes information that has no connections. When you learn something as isolated words, blockchain is a distributed ledger technology, your brain has nowhere to store it except as a string of syllables. There's no web of meaning, no connection to things you already understand, no link to situations where you'd use it. So your brain does what it's designed to do. It assumes this information doesn't matter and deletes it to make room for things that do. The students in Brazil could pass exams because exams tested recitation, but the knowledge evaporated immediately because it was never connected to anything real. You've experienced this exact pattern. You crammed for that certification exam, passed with a good score, then couldn't answer basic questions about the material 2 months later. Not because you're forgetful, because you learned words without weaving them into your existing knowledge structure. Feynman discovered the mechanism. Now, here's what he did about it. He started teaching differently. Instead of defining terms, he'd describe phenomena first. Instead of equations, he'd start with observations anyone could make. For polarized light, he didn't begin with Brewster's angle. He started by asking, what happens when you look at a lake on a sunny day wearing polarized sunglasses? Why does glare disappear when you turn your head? Students could visualize this. They'd seen it. Now they had a hook. Then he'd explain, light waves vibrate in different directions. Water surfaces reflect waves vibrating horizontally more than vertically. Your sunglasses block horizontal vibrations. That's why glare disappears. Same physics, completely different approach. He started with something concrete, something connected to experience, then built up to the technical term. Students started understanding, not memorizing, understanding. Feynman later refined this into what's now called the Feynman technique. The principle is simple. If you can't explain something in simple language, you don't understand it. Not simple as in dumbed down. Simple as in connected to things anyone can grasp. This is why you forget most books you read. You highlight impressive-sounding sentences, but never stop to translate them into your own words, connected to your own experience. The highlights sit there, disconnected, until your brain sweeps them away. This is why you forget most courses you take. The instructor presents frameworks and models, you copy them down, but you never build the bridge between those abstractions and your actual work. Your brain is doing its job. It's eliminating noise. The problem is, your learning method makes everything look like noise. But there's a deeper issue Feynman uncovered in Brazil. He noticed something strange about which students struggled most. The students who'd spent the most time studying, the ones with the most notes, the most underlines, the most hours logged, often performed worst on his understanding tests. They'd been reinforcing the wrong thing. Every hour spent memorizing disconnected facts was an hour spent teaching their brain that this is what learning looked like. They'd built a skill, just the wrong skill, the skill of recitation without comprehension. You've built this skill too. Years of education trained you to do it. Highlight key passages, copy down important points, memorize definitions, reproduce them under test conditions. This worked in school because school mostly tested recitation. But in your career, nobody cares if you can recite. They care if you can apply, adapt, synthesize, explain. And your brain, trained for decades to store disconnected words, keeps doing what it learned to do. Feynman saw this pattern everywhere once he started looking. Students who could recite Maxwell's equations but couldn't explain why a radio worked. Students who'd memorized thermodynamic laws but couldn't predict whether ice would melt faster in a vacuum. The words were there. The understanding was absent. This is why you can read 3 books on leadership and still freeze in your first management situation. You memorize the principles, provide clear feedback, build trust, delegate effectively, but you never connected them to specific moments, specific challenges, specific conversations. So, when the moment comes, your brain searches for relevant knowledge and finds words, just words. And words don't tell you what to do. Feynman documented his Brazilian experience as a warning, but he also provided the solution. The solution isn't studying harder, it's studying differently. After returning from Brazil, Feynman developed a teaching philosophy he used at Caltech for decades. His lecture series, now published as the Feynman Lectures on Physics, demonstrates the principle in action. He never started with equations. He started with questions anyone could ask. Why is the sky blue? Why does ice float? How does a magnet work? Then he'd build understanding layer by layer, each layer connected to the previous one, each layer testable against experience. His students didn't just pass exams. They retained knowledge for life, because that knowledge was woven into a web of meaning, not stored as isolated facts. Here's what this means for everything you're trying to learn right now. You're probably learning backwards. You're starting with conclusions, the frameworks, the models, the definitions, and trying to memorize them. This is why they disappear. Reverse the process. Start with the problem the knowledge solves. Start with the question it answers. Start with the phenomenon it explains. Before you read another page of that technical book, ask, what real situation would make me need this information? Before you take notes in that workshop, ask, what specific problem at work would this solve? Then, and only then, learn the content. But learn it as the answer to that question, not as isolated information. This is what Feynman did instinctively. It's why he could explain quantum electrodynamics to non-physicists. He never memorized disconnected equations. He built each piece of knowledge onto a foundation of understanding connected to things he could see and test and verify. But there's a second critical step. Feynman's technique requires you to explain what you learned in your own words, as if teaching someone with no background, not summarizing, not paraphrasing, explaining from scratch, using only concepts and words your listener already knows. When you try this, something remarkable happens. You instantly discover the gaps. You'll start explaining, hit a point where you realize you can't actually describe what happens next, and discover you memorize that. Part without understanding it. This is the moment of truth. Most people panic here. They think, I should have understood this. I'm not smart enough. Wrong diagnosis. You found the disconnect before it became permanent. Now you can go back and build the actual connection. Feynman did this constantly. In his documented conversations with colleagues, he'd explain ideas using everyday analogies. When the analogy broke down, he knew he'd hit a boundary of his understanding. He'd say, I don't actually understand that part yet. Then he'd go figure it out. This habit, explaining in simple terms, finding the gaps, filling them, is why Feynman retained knowledge that others with similar intelligence forgot. The mechanism is simple. Your brain remembers information woven into a connected structure. It deletes information stored as isolated units. So, here's your system, starting Monday morning. Pick something you're trying to learn right now. A book, a course, a skill for work. Before you consume more content, stop and ask, what problem does this solve? Write down a specific scenario where you'd use this knowledge. Make it concrete. Not, I'll use this for better decision making. Instead, I'll use this next time I have to choose between 2 job offers. Now, as you learn, constantly test comprehension. After each section, close the book and explain it out loud to an imaginary person who knows nothing about this topic. Use only words they'd understand. No jargon unless you define it in their terms first. If you need to say quantum superposition, explain it as the particle exists in multiple states at once, like a coin spinning in the air being both heads and tails until it lands. When you hit a part you can't explain simply, stop. Don't move forward. That's the disconnect. That's the part your brain will delete next week. Go back to the source. Read it again. But this time, build the bridge. Connect it to something you already understand. Find the analogy. Describe what you'd see, hear, feel if you encountered this in real life. Only when you can explain it, simply do you move on. This feels slower than highlighting and note-taking. It is slower, but highlighting is fake progress. You're moving through pages without learning anything that lasts. Feynman's method is real progress. You're moving through less content, but you're actually learning it permanently. 3 months from now, test yourself. With the highlighting method, you'll remember almost nothing. With Feynman's method, you'll be able to explain the core concepts without reviewing, because they're not stored as words anymore. They're woven into your understanding of how things work. There's one more documented insight from Feynman's Brazil experience that changes everything. Near the end of his year there, he gave a lecture to the faculty about what he'd observed. He explained the problem, students memorizing without understanding. He showed them the evidence. Perfect recitation, 0. Application? The faculty agreed completely. They nodded. They said yes, this is a serious problem. They thanked him for identifying it. Then they went right back to teaching the same way. Feynman realized something crucial. The faculty had memorized his critique without understanding it either. They could recite his concerns. They just couldn't connect them to their own behavior. This is the meta lesson. Knowing about the problem doesn't fix it. You can read this entire script, understand intellectually why you forget things, and still not change your learning method. Because understanding intellectually and understanding in your bones are different things. You need to experience the technique working. You need to try explaining something you know and feel the moment you hit the gap. You need to fill that gap and feel the difference between words you memorized and concepts you actually understand. That experience is what changes behavior, not the intellectual knowledge that you should change. So here's your single action step. Tomorrow, take something you learned recently, anything, a chapter from a book, a concept from a course, a skill you're developing. Sit down with a blank page, no notes, no references, just your memory. Try to explain it to someone who knows nothing about the topic. Write it out or say it out loud. Use only words they'd understand. You'll hit the gaps within minutes. Those gaps are what your brain is about to delete. Now go back to the source. But this time, build the bridge. Connect the concept to something concrete. Find the analogy, make it real, then try explaining again. Keep cycling until you can do the entire explanation without gaps, using only simple language. This one exercise will reveal more about your learning gaps than a month of highlighting and note-taking, and it will teach you in your bones the difference between memorizing and understanding. Feynman spent his career proving a simple truth. If you can't explain it simply, you don't understand it yet. Not, you're not smart enough. Not, it's too complicated. You just haven't built the connections yet. Your brain isn't failing you. It's doing exactly what it's supposed to do, discarding disconnected information to make room for knowledge that actually matters. The question is, are you giving it knowledge or just feeding it words?
All right, so you think you're touching something. You're sitting in a chair, you feel it, seems obvious, seems like the most basic thing in the world, the most fundamental experience you can have. But you're not. You've never touched anything. Not once in your whole life. And I mean that literally, physically, actually. Never touched a single thing. Now, before you tell me I'm crazy, this is just physics. This is what's actually happening, and it's much stranger than whatever you learned in school, much stranger than the picture you have in your head of what matter is. So, look, atoms. Everything's made of atoms. You know this, fine. They taught you this when you were a kid. But what nobody really emphasizes, what gets lost somehow, is that atoms are almost entirely nothing. I mean really nothing. Not mostly stuff with a little space, mostly space with almost no stuff. The nucleus, that dense little thing in the center where almost all the mass lives. It's tiny, unbelievably tiny compared to the atom itself. If you made it the size of a fly, just a little house fly sitting here on the table, the electrons would be way over there, across a football field, maybe further, maybe out in the parking lot. And between the fly and those electrons, nothing, no stuff, just space, just emptiness, just distance with nothing in it. And yet here you are, feeling solid. The chair feels solid. The floor feels solid. How can that be if you're mostly empty space sitting on something else that's mostly empty space? Two clouds of nothing pressing against each other, and somehow you don't fall through? This is the question. This is where it gets interesting. See, the space isn't really empty, and that's the mistake everyone makes when they first hear about atoms. They think empty means nothing's happening, nothing's there, it's just void waiting to be filled with something. But something is happening. Something is very much there. Field, electric fields everywhere, extending through that space, filling it with invisible influence. Every electron, every proton, they don't just sit there being little balls, little points of stuff floating in nothing. They reach out. They create this influence around them that extends through space in all directions. And that influence is the field, the electric field, the electromagnetic field. And look, the field is real. People get confused about this. They think it's just a mathematical trick, a convenient way to calculate things, a shortcut we invented because the real explanation is too complicated. No, no, no. The field is there. It exists in space. It carries energy. It carries momentum. It does things. You can't see it, but you can see what it does. And what it does is hold the world together. So you've got atoms, and around each atom there's this electric field spreading out in all directions, getting weaker with distance, but never quite disappearing, extending in principle all the way across the universe. When two atoms get close, their fields meet first. The fields start interacting before the atoms themselves get anywhere near each other. And here's the thing about electric fields. The electrons in your hand, the ones on the outer edge of your atoms, they're negative. The electrons in the table, same thing, negative, same charge. And what do same charges do? They repel. They push each other away. They say, no, you can't come here. This space is mine. Go somewhere else. So, when you press your hand on a table, what you feel, that pressure, that resistance, that sensation of solidity, it's not atoms hitting atoms. It's not little balls bouncing off other little balls. It's fields pushing against fields, electromagnetic repulsion. The electrons get close enough that their fields overlap, and the fields say, no, absolutely not. You shall not pass. And you feel that as touch. You feel electromagnetic repulsion, and your brain interprets it as contact, as solid matter, as the experience of touching something. But the atoms never meet. There's always a gap. Always, always, always a gap. Your electrons and the table's electrons never make contact, never actually reach each other. They're always separated by this buffer of electromagnetic force, pushing them apart. You're floating right now. Did you know that? You're floating a tiny, tiny distance above your chair, suspended by electric forces, hovering on a cushion of electromagnetic repulsion. You've been floating your whole life. You never knew it. Every time you thought you touched something, you were hovering just above it, pushed away by invisible forces. Now you might say, fine, but what's the difference? It feels like touching. It works like touching. Who cares about the details of what's happening down there at that scale? And okay, from a practical standpoint, from the standpoint of getting through your day and sitting in chairs and picking up coffee cups, it doesn't matter. You can ignore all this and live your life just fine. But if you want to understand nature, if you want to know what's actually going on, if you want to see reality clearly instead of through the fog of everyday assumptions, this is it. This is the beginning.
The solid world isn't solid. Touch isn't touch. And the space between atoms, that vast emptiness that makes up most of what you are, it's not empty at all. It's full of fields. And those fields are full of something even stranger. So the space between atoms is full of fields, electric fields, electromagnetic fields, reaching out from every charged particle, filling what looks like emptiness with invisible influence. But that's not the end of the story. That's not even the strange part yet. What happens when you take everything away? Not just the atoms in air, not just the dust and the molecule, everything. You pump all the matter out of a region of space. You create the most perfect vacuum you possibly can. And then you ask, what's left? Nothing, right? Has to be nothing. You took everything out. That's what vacuum means. That's what empty means. There's nothing there anymore. Wrong. Can't be nothing. Nature doesn't allow it. The universe refuses to be truly empty anywhere, ever, under any circumstances. See, quantum mechanics has this thing called the uncertainty principle, and most people have heard of it, but they don't understand what it really means. They think it's about measurement, about how looking at something changes it. And okay, fine, that's part of it, but there's something deeper. The uncertainty principle says you cannot know certain pairs of properties exactly at the same time. Position and momentum, you can't pin down both, but also energy and time. You cannot have a region of space with exactly, precisely zero energy for any extended period of time. It's not permitted. The equations forbid it. The mathematics of quantum mechanics says no, you don't get to have perfect emptiness. That's too exact, too precise. Nature doesn't work that way. So what happens instead? The vacuum fluctuates. Even with nothing in it, it's doing something. It's restless. It can't sit still. Little pairs of particles pop into existence out of nowhere. A particle and its antiparticle, an electron and a positron, a quark and an antiquark. They appear spontaneously in empty space. They exist for an incredibly short time, so short you can barely define it, and then they find each other and annihilate and vanish, gone, like they were never there. Virtual particles, they're called. Virtual because you can't catch them directly. You can't put them in a bottle and look at them. They exist for too short a time to observe in the normal way. But they're there. They have effects, real, measurable effects. Now people ask, okay, fine, but where does the energy come from? You can't just make particles out of nothing. That violates conservation of energy. You can't get something from nothing. And it's a good question. It really is a good question. But here's how it works. The uncertainty principle says you can borrow energy from nowhere as long as you pay it back fast enough. The shorter the time, the more energy you can borrow. It's like taking money from a bank and returning it before anyone checks the books. As long as the accounting balances out in the end, as long as the energy gets paid back before the universe notices the debt, it's allowed. Virtual particles pop into existence on borrowed energy, and they pay it back by annihilating. The debt gets settled. Conservation of energy is satisfied, on average, over time. But at any given instant, there's this frenzy of borrowing and repaying happening everywhere in space. Nature runs on credit at the smallest scales. Temporary violations everywhere, constantly, as long as everything balances out in the end.
And this isn't some theoretical speculation, some mathematical game physicists play because they're bored. We can measure this. There's an experiment called the Casimir effect, and it proves the vacuum is not empty. You take two metal plates, very thin, very flat, and you put them close together in a vacuum, almost touching, but not quite, just a tiny gap between them, smaller than the width of a hair, as small as you can manage. And they attract, they pull toward each other. Not because of gravity. Gravity's way too weak to notice at that scale. Not because of static electricity. Nothing's charged here. The plates are neutral. The space is empty. There's no reason for them to move. But they do. They pull together. And the reason is virtual particles. See, virtual particles have wavelengths, like waves in the ocean have wavelengths, different sizes of oscillation. And when the plates are very close together, some wavelengths don't fit in between. It's like trying to fit a long wave into a short space. It doesn't work.
Those particular virtual particles can't exist between the plates. So, there's fewer virtual particles popping up between the plates than outside them. More activity outside, less activity inside. And that imbalance creates pressure. More pressure pushing the plates together from outside than pushing them apart from inside. The plates move toward each other, squeezed by empty space, pushed by nothing. This has been measured, precisely measured. The force is exactly what quantum mechanics predicts. The vacuum is not empty. The vacuum pushes things around. So, think about the space between atoms now. Got it? The space inside you. It's not just fields sitting there quietly humming along. It's churning. It's frothing. Virtual particles are appearing and disappearing constantly, right now, inside your body, in every bit of empty space within every atom that makes up your hand, your heart, your brain. The emptiness inside matter is not empty. It's the busiest place in the universe. Creation and destruction happening billions of times per second in every cubic centimeter of space. And this is everywhere, not just in atoms, not just in matter. The space between here and the moon, the space between stars, between galaxies, the vast stretches of what looks like nothing. Same thing. Virtual particles appearing and vanishing. The vacuum churning and fluctuating and refusing to be still. There is no quiet place in the universe. There is no place where truly nothing happened. You cannot find nothing. Nowhere in the entire cosmos is there actual emptiness. Physics won't allow it. So, the vacuum seethes with activity. Virtual particles everywhere, all the time, popping in and out of existence faster than you can imagine. The emptiness between atoms, between stars, between galaxies, it's all the same, all churning, all restless. And this changes everything about how you should think about matter, about space, about yourself. See, people talk about the vacuum like it's the absence of everything, the default state, the boring part, what you get when you take away all the interesting stuff. Clear the stage, and what's left is nothing, right? Empty space waiting for something to happen in it. But that's completely backward. The vacuum isn't absence, it's foundation. It's not what you get when you remove everything. It's what everything comes out of. The vacuum is the ground state of reality, the lowest energy configuration of the fields that fill all of space. And that lowest energy still can't be zero. Particles aren't stuff that exists in empty space. Particles are excitations in fields, and those fields exist everywhere, including in the vacuum. A particle is just the field doing something more than usual, vibrating a little harder, carrying a little more energy than the quiet background hum. Matter isn't stuff sitting in empty space. Matter is space doing something different, a different configuration of the same fields that make up the vacuum. You and the empty space next to you are made of the same thing, the same fields, the same quantum substrate. You're just arranged differently. You're a pattern, a ripple, a fluctuation that got complicated and started walking around and asking questions about itself.
The vacuum could have been you if things had gone differently. And someday, when those patterns disperse, when the arrangement that calls itself you stops being arranged that way, you'll be vacuum again. The fields you're made of will still be there, just in their ground state, just doing the minimum, waiting to become something else. Now let's go back to you sitting in your chair and put it all together. What's actually happening? You're a collection of atoms, right? That's the first level. Those atoms are held together by electromagnetic forces, by fields, pulling electrons toward nuclei and pushing electrons away from each other. Chemical bonds, molecular structures, all of that is electromagnetic fields doing their thing. But those atoms are mostly empty space. The nuclei are tiny, the electrons are far away, and in between, there's this vast emptiness filled with electric fields. And you're not falling through the chair because your electric fields are pushing against the chair's electric fields. Electromagnetic repulsion. That's what solid feels like. That's what touch is. But inside all that empty space, inside every atom, inside every gap between every particle, the vacuum fluctuates. Virtual particles flash in and out of existence. The quantum foam bubbles away constantly, everywhere, all the time. So, you're not just atoms. You're atoms that are mostly fields that are full of virtual activity, patterns on top of patterns on top of a churning quantum sea that can never be still, and there's no bottom to it. That's what gets me.
You zoom in, looking for solid reality, looking for the thing that everything else is made of, the foundation, the bedrock, and it keeps dissolving. Atoms aren't solid, they're mostly empty. The empty isn't empty, it's full of fields. The fields aren't static, they're fluctuating with virtual particles, and the particles themselves, when you look closely, they're just excitations in other fields. It's fields all the way down. There's no point where you hit something solid and say, here, this is what it's really made of. This is the ultimate stuff. It's like looking for the bottom of a lake and finding out the lake goes down forever. At some point, you have to accept there is no bottom. There's just water all the way down, getting darker and stranger the deeper you go, but never hitting rock. Reality is like that. No foundation, no stuff, just activity, patterns, relationships, things interacting with other things, and those things themselves being nothing but interactions. The universe isn't made of stuff. It's made of happening, events, processes, the feeling of solidity, the experience of touching something, of being something. It's all patterns in fields that extend across all of space. And those fields connect everything. The electromagnetic field in your hand is the same field as the electromagnetic field in that distant star. Same field. Not a copy, not a similar field, the same one. It extends continuously through all of space, and particles are just places where that field is doing something interesting. You're not separate, universe. You can't be. You're a localized pattern in fields that extend everywhere. You're connected to everything by the very medium that makes you up. So, what's between the atoms? What's in that vast space that makes up most of what you are? Fields. Real physical fields that carry energy and exert forces. Virtual particles bubbling up from the quantum vacuum, appearing and disappearing, borrowing energy and paying it back. Activity and fluctuation and potential. Not nothing, never nothing. The universe doesn't do nothing. It can't. Emptiness is forbidden. Perfect stillness is impossible. The vacuum itself is alive with creation and destruction at scales too small and too fast to see. And when you finally understand that, when it really sinks in, the world stops looking like a collection of solid objects sitting in empty space. It starts looking like what it actually is, a web of interactions, fields influencing fields, patterns emerging and dissolving, with no hard edges anywhere, no true emptiness anywhere, no foundation except the churning quantum vacuum that can never sit still. The space inside you and the space between galaxies, it's the same space, made of the same stuff, doing the same things. The only difference is the pattern. The only difference is the arrangement. That's what you are. That's what everything is.